dose as we're going to get on the space station program in the present decade without going anywhere. So this concern that we have to not go to Mars until we have an impossible propulsion system because we have to protect the crew from radiation is belied by the fact that we're actually going to subject our crews to that much radiation over the coming decade without going anywhere. So that is my concern with this. Vasimir, as a technology that someone might want to spend money on to advance, fine. It could be an interesting addition to a toolkit. Conceivably, for certain outer planet missions, it might be superior than an ion engine. But it won't get us to Mars quickly, and especially in view of the fact that there is no program to attempt to develop 200,000 kilowatt space nuclear power. The entire subject is irrelevant. Okay? So I think what we need to do, we need to put Vasimir in perspective as an interesting technology to be worked on in labs, but push on to Mars without it. Thank you.
Thank you for your perspectives. We're going to now open it up to questions. I'd like to ask if you could please use the microphone in the middle, line up. We only have about 10 minutes for questions, unfortunately. You have an hour break for lunch after that, so I'm going to limit the questions as well. So please, begin.
I'd kind of like to reiterate what the panel was saying. I've designed a lot of microwave circuitry and power circuitry, and just from a standpoint of the DC to DC converter, as Dr. Landis will reinforce, anything going into space has to have 80% efficiency right off the bat, so that blows away your 90% efficiency on your DC to RF. And then you start getting into the world of the RF circuitry, and with traveling wave tubes designed for radar, that yes, you can get 90%, but those aren't continuous duty type of electronics. They're pulsed, which, if I understand the Vasimir correctly, it would have to be continuously operating at 90%, and that would shorten the lifetime to almost nothing in a hurry.
Yeah. Typical experimental numbers for electric propulsion systems end up at about 50% electrical efficiency. So out of the whatever kilowatts you're getting out of your reactor, only about half of that goes into propulsion. There's a lot of people who'd like to find better numbers, but that's what we're getting at the moment, about 50%.
Okay. If we resurrected the old NERVA that was canceled in 1973, or something similar, could we get to Mars more rapidly than with the chemical solution?
I say yes, we probably would be able to get to Mars more rapidly than the chemical solution. I didn't go through the full table, but the nuclear thermal design point I mentioned with the thrust to weight ratio about 6 2/3, and that was a 40,000 pound thrust unit. And with that class of nuclear thermal rocket, I think, Bob Zubrin would agree, we could maybe move a little faster.
Even if also for this technology there is some points that are put under the carpet concerning performance, there is some kind of losses. First, because you cannot perform tests in the open air, you are obliged to limit the thrust of the engine you develop and you test. And so you augment the gravity losses during the propulsive maneuver to propel your spacecraft to Mars, so there is losses. Second, for safety reason, you cannot start for a 200-kilometer altitude orbit. You have to start for a much higher, so your launcher from Earth has a loss of performance also. And third, the engine is much heavier than a chemical engine. The tanks are much larger and heavier also. So we have a gain of performance, but not so much as the ISP could tell.
Thank you. Thanks.
Well, somebody must be a really good salesman that this has gotten any traction at all. So I don't know how if this gets sold to the leadership. But has anybody figured out how long it would take, even if a series of unlikely miracles happened and you had this system, how long would it take you to get through the Van Allen belt where you get a significant dose of radiation if you spend too long there?
Well, once again, it all depends on alpha. Okay, with realistic alphas, it would take months. Now, some advocates of this technology will say, well, we will never bring it down. We'll have it stationed, up at Lagrange points, and we'll go to it with taxis and, with chemical propulsion. And you can get into these sorts of complex architectures to avoid things, but things get more and more complex, and you just move further and further away from the realm of spacecraft engineering that we actually know how to do into this sort of parallel universe of the magnificent activities in space.
The stuff that us science fiction writers really love.
All right, thank you.
Thank you.
This is for any of the panel members. What's the state of the art of, say, solar thermal propulsion systems, and would that be of any benefit for delivering cargo to Mars as, say, a second-generation vehicle? And what about using solar sails? I know you need a humongous sail, and it takes long trip times also. But what about those two technologies, solar thermal propulsion and solar sail propulsion?
Solar thermal propulsion sort of got stalled. There was a lot of good proposals to do that in the 1980s, and there was even a Air Force-sponsored program to try and develop it in the 1990s. But it turned out to be sort of hard to find a good mission for it. In many ways, it's a very complicated technology. You have to have very large solar concentrators, and typically the proposals propose large inflatable concentrators, and they have to be pointed pretty accurately at the sun. And then there's a lot of sort of technical details about transferring the solar energy to the hydrogen. Another point is that, like nuclear thermal propulsion, solar thermal propulsion really only works well with hydrogen as the fuel. A nice thing about the ion propulsions, or for that matter even Vasimir, is that you can use much more dense fuels. The ion propulsion typically uses xenon, which is actually a pretty heavy gas. It's, of course, it's liquid when we use it, supercritical liquid. Whereas hydrogen is tough stuff to work with. It has density lower than styrofoam, and you have to keep it very cold. So solar thermal mostly stalled. It might be a good technology for cargo, because like all the electric and non-chemical propulsion systems, the amount of thrust you can get is proportional to how much your energy source is, which means it's proportional to the area of that solar concentrator mirror. So unless you have a huge mirror, you're not getting a whole lot of thrust. Solar sails, on the other hand, were very popular, and still are popular with the Planetary Society. They're a very interesting technology. This is a technology that has technically infinite specific impulse. You get no fuel use for your momentum. The downside of that is the thrust is very, 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 very low. It turns out thrust level and specific impulse are opposites. They're canonically conjugate variables. You can't get them high both at once. Solar sails are phenomenally good for very high delta V missions if you want to wait a very long time, years. If you're going to the stars, there's a lot to be said for solar sails. For going to Mars, well, sort of work out the numbers. It's about 6.5 newtons per gigawatt of thrust. Newton, 4.5 newtons is a pound. So a little over a pound of thrust for a gigawatt of power, of solar power. And the solar energy is about 1.3 gigawatts per square kilometer. So square kilometers of sail give you just a little bit of thrust. So it's a great thing if you don't care how long it takes to get there, because you can get there with no propellant use at all, zero. but it takes a long time because it's a low-thrust system.
Okay, thank you for your questions. I'd like to thank our panel, Dr. Robert Zubrin, Jeffrey Landis, Richard Heidman, and Rob Terry for their input. And I think it sounds like it depends on the mission, and of course the mission that we're focused on here is sending humans to Mars. Silver bullet or hoax, let you decide. Thank you. See you again back here at 1 p.m.